All right, so before we get into 9.2 in earnest, let me ask you if you remember something. Oh boy, here we go. I'm expecting you to remember something. Well, it's just a question. You could say no. Remember on the last test when we had something like 3x cubed plus 2x squared minus 5x plus 1 divided by 2x minus, or let's just say divided by x minus 1. Remember when we had that? Phone's away now. We're teaching. We're live. Um, and you could have found the quotient by doing either long division or synthetic division. And I beseeched you, I asked you to write it a certain way before you went to the answer, which was the quotient plus the remainder over the divisor. I asked you to write it as 3x cubed plus 2x squared minus 5x plus 1 divided by x minus 1, and then put your quotient plus the remainder over the divisor. Remember when I asked you to do that? I said, this is an honors class. You should get in the habit of doing that. Okay. The reason you want to do that is because you could think about it entirely differently. Instead of saying, what is this polynomial divided by the polynomial, you could think of it as a brand new function, f of x, that is a polynomial over a polynomial. And it has its own graph with its own features that are different from a cubic polynomial, that are different from a linear polynomial. It taken together gives you a brand new graph, okay? And that's what we're studying in 9.2. We call this type of function a rational function. What do you think the key word in rational is? Actually, it's Al. It's named after some guy named Al. Yeah, no, I'm just kidding. No, you're right. It's ratio. It's a ratio. So what is a rational function? It's nothing more than, we'll say it equals, it's a ratio of two polynomials. It's a ratio of two polynomials. What does it mean, a ratio? Ratio implies what operation? Divide. Very good. It implies divide. It's something compared to something else. Something divided by something else. So this is a rational function. F of x is a rational function. Now, there are certain features that we're going to focus on today. One of the main features is this. You learned in little school that you can't divide by 0, right? You learned that at a very early age. So there is a variable in the denominator. And what value of x, when I plug it in for x and subtract 1, makes the denominator 0? A 1, right? So 1 is not allowed in this function. If you went to the graph of this brand new function and you looked at x equals 1, nothing would be there because it's not, we say, in the domain. It's not in the domain of the function. You can't divide by 0. 1 makes division by 0. 1 is not in the domain. Does anyone know what graphical feature lives there at x equals 1 from past experience? You probably don't have a lot of experience with it. Okay? We get what's called, I'll show you right here. I'll write it. We get what's called a vertical asymptote. Asymptote. It's a pretty cool word. Asymptote. 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 You really have to make that PT sound stand out. Asymptote. Have you heard that word before? Maybe not pronounced like that? Asymptote? Asymptote? Okay. What is an asymptote? Okay, let's talk about an asymptote. Let's define it. An asymptote is basically equal to an imaginary line that the values get closer and closer and closer and closer and closer to, but in this case, I'm going to kind of say, but never, bless you, but never touch. They actually can touch in certain types of cases, but it never settles down. It never settles down to the actual value of 1. Okay? So we can let x get really, really close to 1, right? Let's think of the first number to the right of 1. If I wanted to get close to the number 1 from the right-hand side, what would be a number that's allowed that's not equal to 1, that's just to the right of 1? 1.1. That's pretty darn close to 1. The function's going to live at 1.1. There's going to be a dot. There's going to be a piece of the graph at 1.1 because 1.1 doesn't give us division by 0. But can we get closer to 1 from the right besides 1.1? 1.01, 1.001, 1.00001. You got the idea now, right? 1.000000000. Put as many zeros as you want until you run out of breath, and then say 1, and now you're a point on the graph. The question is, as x gets really, really close to 1, what are the y values doing? Well, that's what we're going to study today, okay? It's kind of a fascinating thing. The parent function here for a rational function p over x, or p over q, sorry, p over q, where p and q are polynomials, we call it the rational function. The parent function for all rational function is this dude right here, 1 over x. This guy is the parent function, but he also has its own name. Why am I writing so thickly here? Ooh, I don't like that. Hang on. Let me back it up here. We call this function the reciprocal function. Here's why we call it the reciprocal function. If we made a t table, right, a t table, and we put in like 1, 2, 3, 4, what do we get? 1 over 1 is 1 over 1, 1 over 2, 1 over 3, 1 over 4. You get the idea? What does it do to the input? It flips it, right? And it gives you the output. That's its reciprocal. What do you get when you plug in a 0? What's the reciprocal of 0? 1 over 0? Is that allowed? No. In fact, is 0 even in our domain? No, because if I plug in a 0 for x, I get 1 over 0, and I can't divide by 0. So guess what this graph has at x equals 0? I just said it up above. It's a vertical asymptote. You can just say asymptote. You can kind of forget the p's there. Asymptote, asymptote. It has a vertical asymptote at 0, okay? 0 is not allowed. But all the other numbers in the whole wide world are allowed. Every single number on the number line has a reciprocal except 0. 0 is the only one without a reciprocal, okay? Now, here's what the graph looks like. The parent function for 1 over x looks like this. It actually takes the shape of what's called a hyperbola. It has a hyperbola shape. Okay? You don't need to know that, but I'm throwing that out there because we have a parabola. You know a parabola. A quadratic has a parabola shape. This graph, the reciprocal function, which is the parent function for all rational functions, is a hyperbola shape. Okay? A hyperbola shape kind of looks like an X. This one's kind of rotated, right? If you made an X like this and then you rotated it, that's what a hyperbola looks like. What's a rational function again? I forgot what I was saying. What is a rational function again? I don't want to keep going if we don't even have the basics down. A rational function is a ratio of two polynomials. Very good. Okay. The reason 1 over x is the parent function for all polynomials is because it's the simplest one. It's the polynomial 1, which is a constant monomial. That's really a degree 0 polynomial, all over x to the first, which is your linear monomial. It's the most basic polynomial over polynomial. Remember, constants are considered polynomials too. Okay, so a rational function is a ratio of two what's? Polynomials. Okay, good. Now, the two important features that we want to really focus on here are the vertical asymptote. I guess I should switch to something thicker now. There is a vertical asymptote. I'm going to call that a VA, a vertical asymptote. I'm going to abbreviate that vertical asymptote. We draw the dotted line because it's not really part of the graph. It's an imaginary line that helps us see what the graph is doing. So notice, as I plug in values just to the right of 0, in this case, 0 is not allowed. So like we did with 1 on the previous example, I can plug in a value just to the right of 0. What would be the first number to the right of 0? Since 0 is not allowed, the numbers to the right of them are. What's the first number to the right of 0? 1? No, 0.1, right? Or can we get closer to that? 0.000001, okay? Now, let's think about that. If I let it be 0.1, another name for 0.1 is 1/10, yes? We call it 1/10. What would be the reciprocal of 1/10? 10, right? You just flip it. What's the reciprocal of 1/10? 10. Okay, now if I get closer to the x-axis or the y-axis, 0.01, that's really read as 1/100th, right? 1/100th. What would be the reciprocal of 1/100th? 100. Ooh, that's bigger now, isn't it? Let's get even closer to 0 from the right-hand side. 0.001. That's read as 1/1000th. What's the reciprocal of 1/1000th? 1,000. Do you see what's happening to my y values as I get closer and closer to 0 from the right? The reciprocals are being what? Getting what? Bigger and bigger and bigger and bigger. Now, here's the ultimate question. How close to 0 can I get from the right-hand side without actually getting there? Infinitely close. Very good. I can get infinitely close to 0 from the right-hand side by just adding as many zeros as I want and putting a 1. And as I do that, my y values are continuing to do what? Infinitely. Getting bigger and bigger and bigger, infinitely large. So here's the behavior at a vertical asymptote. As we approach 0 from the right-hand side, the y values are approaching infinity. That's what a vertical asymptote does. The graph never touches 0 because 0 is not allowed. It's undefined. But as I get closer and closer to 0 from the right, the reciprocals get bigger and bigger and bigger. Okay. Now what happens as I approach 0 from the left? -1/10th, -100th, -1,000th. What's the reciprocal of -1/10th? -10, right? What's the reciprocal of -100th? -100. So it's doing the same kind of thing on the left-hand side. It's just the values are going to negative infinity. They're getting infinitely small towards negative infinity. So that's the first behavior you need to recognize about this function. X is not in the domain, but there's a vertical asymptote. X equals 0 is not in the domain, but there's a vertical asymptote at 0 that forces the y values up on the right and forces the y values down on the left. Okay, now there is another asymptote on this graph. Can anyone guess where the other asymptote is? You can kind of tell by the shape. The x-axis, also known as what? Very good. We're going to call it a horizontal asymptote. So go ahead and add this. Vertical asymptote at x equals 0. I'll put in parentheses here, that's the y-axis. Now I'll change flavors here to, what's a good comp? It's green. Okay. If you draw a horizontal line now on the x-axis, you get what's called a horizontal asymptote, which I'm going to call an HA. Aha! Yeah. And it's at y equals 0, which is the x-axis. Now let's think about what's happening there. These are the end behaviors of the graph. As I go out to the right, my x values can be anything, right? As long as x isn't 0, x can be any number. But as I go further and further down the x-axis, my numbers are getting bigger, right? Like, let's say I'm out here at x equals 100. I plug it in. What's the reciprocal of 100? 1/100th. That's kind of small, right? What if I keep going out to like 1,000? I'm way out here to 1,000. What's the reciprocal of 1,000? 1/1000th. That's even smaller, isn't it? Whoo, I'm getting smaller. What if I come out here to 1,000,000? What's the reciprocal of 1,000,000? 1/1,000,000th. What's happening to my y values as I continue to go out to the right? They're getting smaller and smaller and smaller and smaller, approaching what? They're approaching 0. Are they ever going to equal 0? They'll never equal 0 because my x value can go on forever. So it never equals 0. It just approaches 0. Okay. So this graph, as you go out to the right, starts leveling off towards the x-axis, but it never equals 0. Okay. So here's the idea that we've already established. This is pretty important. The reciprocal of a very, very small number is a very, very what number? Big number, right? And the reciprocal of a very, very big number is a very, very what? Small number. That's hugely important. Because what we say in calculus is this. 0 is undefined. So it has no reciprocal. It's 1/0. It's undefined. But we can talk about ideas. Because the reciprocal of a very, very tiny number that's practically 0 is a very, very huge number, might as well be infinity, and vice versa. We say that the reciprocal of 0 is infinity, and the reciprocal of infinity is 0. The reciprocal of 0 is infinity, and the reciprocal of infinity is 0. What's the reciprocal of 0? Infinity. And what's the reciprocal of infinity? 0. Yeah. Okay. That's weird cool, right? Yeah. What? Bless you. What happens as we go out to the left? Negative 10, negative 100, negative 1,000, negative a million. What's the reciprocal of negative a million? Negative 1 over a million, right? Which is a negative number. It's still below the x-axis, but it's very, very small. It's almost zero, right? So what's the behavior over here on the left? As x goes to negative infinity, we approach zero from underneath, from the negative side. So there's two asymptotes. The vertical one, as we approach zero from the right, it goes to infinity. As we approach zero from the left, it goes to negative infinity. And then the end behaviors, as x goes to infinity, we approach zero from above. And as x goes to negative infinity, we approach zero from below. That's what the asymptote does. The graph will never touch the x-axis. The graph will never touch the y-axis. Okay? They're asymptotes. And then, of course, we get this cute little graph in between that exists in quadrants 1 and 3. And there you go. There's your parent function. Let's go ahead and talk about domain and range specifically. The domain in set notation is everything but 0. In interval notation, of course, you just step over it. What do we add to our interval notations? X epsilon. Very good. Let me add that. Okay. X epsilon. And then over here, we'll do Y epsilon. You can add that to it. Very good. We're learning. I feel like we're making progress. Now, the vertical asymptote, the equation of it is x equals 0, right? This is the y-axis. And we're gonna call vertical asymptotes VAs. I'm gonna abbreviate them VAs. Feel free to abbreviate them VAs as well on your quizzes, on your tests. That's fine. A horizontal asymptote, that's going to be your x-axis, and we abbreviate that as HA. Ah! I like saying that. Okay. It's almost like there should be another A in front of there, like aha, right? But it's just ha. That was funny joke. Ha. Me caveman. Me laugh. Ha. LOL. Not quite the same. All right. So this is kind of discombobulated here, but it's all there. So let's look at the left part. This is how we write it for now. In pre-cal, we'll talk about a limit notation, but for now, we write it like this. We're used to this. As x arrow in negative infinity. That means as x approaches negative infinity. As I go out to the left, my y values, the function values, are approaching what? 0. And guess what this little negative sign means? From the negative side of 0, which means from below. We saw that on the graph, right? As we went out to the left, forever and ever, we approach 0 from below. Now, the counterpart to that, for some reason, we have to go to this diagonal over here. I don't know why they're not lined up left to right. As x goes to positive infinity, as we go out to the right, the y values, the function values are still approaching 0, yes, but now the little plus sign means where? From above. Absolutely. From above. Okay, that's the horizontal asymptote. HA, HA, if you want to label it. All right, now let's look at the other one. As x goes to 0, and this negative means from where? From the left of 0. What do we say? As we approach 0 from the left of 0, what are the y values doing as we approach 0 from the left of 0? Yeah, go on the graph and just take a ride. You're falling pretty fast. You go to where? Negative infinity. Okay? Now jump over here. The right part, as x goes to 0 from the right. This is the first one we analyzed. As x goes to 0 from the right, what are the y values doing? They're going up, right, to positive infinity. So notice the numbers are switched. In one of them, the x values are 0, and the y values are plus or minus infinity. And on the other one, the x values are plus or minus infinity, and the y values are 0. You just got to keep them straight, right? Okay. Pretty cool stuff. Wacky cool. What's the reciprocal of 0 again? I keep forgetting. Infinity. And the reciprocal of infinity is 0. They're each other's reciprocals. Absolutely. All right, now we're going to go ahead and start by sketching simple transformations of this parent function 1 over x. Okay, that's what we're going to start with. And the transformations are going to look the same as they have all year long. We're going to put it in this format right here. Now, I don't like this 1 over b right here. It really should be just the letter b. So let's do this. Let's take your whiteout tool, your white pen, and we'll scratch out the 1 over b. I don't like that. Whoever wrote these didn't know what they were doing. And we'll put a B there if we want so badly. We'll put a B there. Now this is standard transformation form. Standard transformation form. We've seen that before with vertex form. Okay, it's like vertex form. Except unlike a parabola that had a vertex that we could track, we could see where did the vertex go, and then from there we draw it going up or down. Guess what the main two features we're going to be keeping track of on this graph are? Anyone want to guess what the main two features of this? There's no vertex here to keep track of. When we move it left, right, up, or down, not the x and y intercepts because there's no x and y intercepts, but the two, don't try too hard, the two what? Asymptotes, right. So when we do a transformation of a rational function, we want to follow the asymptotes. If you know where the asymptotes move to, you know what kind of the graph looks like. It's going to live in quadrants 1 and 3, or sometimes if there's a reflection, it's going to be in 2 and 4, okay? So here's standard transformation form. The A in front is the same it's always been. If it's bigger than 1, it's a vertical stretch. If it's between 0 and 1, it's a vertical compression. That just makes the graph steeper or less steep. Kind of hard to show that. But what if A is negative? What does the negative A in front do to any graph, including 1 over x? Reflects it across the x-axis. Okay, let's write that down. If A is negative, if A is less than 0, it's an x-axis reflection, just like always. Doesn't change. But let's see what that would do to the parent function. If I take that blue and I reflect it across the x-axis, now it lives down here. And then the blue in quadrant 3, when I reflect it across the x-axis, looks like that. So my new graph, if there's ever a reflection across the x-axis, is going to now live essentially in quadrants 2 and 4 instead of 1 and 3. Yeah, you see that? So this is why it's important to know where the vertical asymptotes go. Once you move the vertical asymptotes, it's either going to live over here in your new quadrants 1 and 3, or it's going to live over here in your new quadrants 2 and 4, the quadrants that are made by the asymptotes themselves. Okay? And then, of course, we can draw it steeper or less steep. Now, we don't see B a lot, but what is B? B is your horizontal compression factor. What if B is less than 0? What does that do? Well, okay, if B is bigger than 1, it's actually a horizontal compression. Remember, it's the opposite. And if B is between 0 and 1, which is a small number, it actually makes it wider. So it's the opposite of what it appears. But what if B is negative? That's a y-axis reflection. Yeah, let's talk about that. Y-axis reflection. What would the graph look like? Well, the blue graph in quadrant 1, if you reflected it across the y-axis, would now live over here in quadrant 2. So you'd see this piece, but it didn't come from this blue piece, it came from that blue piece. And then the piece in quadrant 3 would reflect across its y-axis, and you get the same piece that we got before in quadrant 4. It's just generated by this guy, not that guy. So the graph kind of looks the same, right? So for this graph, and it's specific only because this is an odd function, origin symmetrical, that a y-axis reflection and an x-axis reflection produce the same thing. Okay, that's pretty cool. Now, the two most important ones, I'll use red, are the minus C. That moves the graph what direction? Left or right, yes? Left or right. Either one. I'm going to put C units, and I'm just going to keep it how we've been doing it. It's the opposite of what it appears, yes? So if you see x minus 1, that's to the right one. If you see x plus 1, that's to the left one. Guess what important feature that's going to move? If I pick this entire graph up, let me get rid of these yellow ones now. If I pick the entire parent function up and I move it left a certain amount, what super important feature did that relocate? The vertical asymptote, right? If I move the whole graph 2 units to the left, my new vertical asymptote is at -2. If I pick it up and move the whole graph 3 units to the right, my new vertical asymptote is at 3. Yes, yes? Oh, that's important, right? Because your new vertical asymptote, This moves the vertical asymptote. It moves the vertical asymptote. It's going to be at now x equals c. It's going to be at x equals c. Now remember, it's x minus, so it's better just to think, oh, did I move it left? It's negative. If I move it right, it's positive. Now let's look at plus d. I'm going to use red for that one as well. Anytime you add d outside the function, what does that do to the entire graph? Up or down? Up or down? D units. And is it the opposite of what appears, or is it exactly as it appears? It's exactly as it appears, okay? Now, let's look at that over here. If I were to take this entire graph and move it up 1 unit, what important feature did that relocate? Which asymptote? The horizontal asymptote, also known as a what? Aha! And my new asymptote, horizontal asymptote, is at y equals 1. What if I move the whole graph down 2 units? It moved the horizontal asymptote, and now it's where? At y equals negative 2. Oh, okay. I'm getting this. This is starting to make a lot of sense, right? So we'll just fill this in here. It's up or down d units, which moves the horizontal asymptote. And now it's going to be at y equals d. Y equals d. Got it? So it's pretty easy. The horizontal shift tells you where the vertical asymptote went. The vertical shift tells you where the horizontal asymptote went. You draw those first, okay, and then you sketch the graph. Now, there's one little thing here, and this is just kind of a subtle thing. The parentheses there are nice because it pulls the a out front, and it leaves us a 1 in the top. With the 1 in the top, we can see that it's 1 over x. There's your parent function. But really, that's the same as a over 1. And I can multiply straight across. What's a times 1? A. So if you see a number in the top that's other than a 1, that's your a value, okay? If you want to pull it out front to the side, you can. Or you can recognize it and leave it in the numerator as your a value. It doesn't matter. They're equivalent to each other, okay? They're equivalent to each other. No, if it were 2 in the top, a would equal 2. Yeah, so like an example, if you see y equals 2 over 3 times x minus 1, that's the same as 2 times 1 over 3 times x minus 1. Okay, a would equal 2. All right. Now, when we sketch the transformations, here's the important thing. We want to graph the asymptotes, both of them. Oops. We want to graph the asymptotes first, every single time. You always want to graph the asymptotes first. Because they're like gravity, the graph is irresistibly pulled toward them. They become guidelines. They become literal guidelines for your graph, okay? So we identify where they went, we sketch them first, and then we just fill it in the 2 opposite quadrants, 1 and 3 or 2 and 4. Let's look at example 1. That's enough preliminary stuff, don't you think? Let's get cooking here. Use the graph of 1 over x, describe the transformations, and then sketch the graph. Okay. Everyone agree this is the parent function transformation of 1 over x? Yeah. What's our a value? 4. You want to leave it in the top or pull it out front? I don't care. Let's leave it. Okay, because then we can just have fewer parentheses. So let's go ahead and describe the sequence of transformations. We still have to do it A, B, C, D format. What is A? It's going to be a vertical stretch by a factor of what? 4. Yeah, easy. Now, you're typically not going to have B values. You're not going to have something multiplied in the X because that's kind of a pre-cal thing. This is still algebra 2. So your B value is typically going to be 1, unless it's a reflection maybe. So that's it for the A and B's. Remember, A and B's change your dilation and your reflections. Now it's just picking it up and moving it. What does the plus 2 do? Left 2. And what does the minus 7 do? Down 7. Yeah, down 7. Down 7. Now, can we figure out where the horizontal and vertical asymptotes are before we even sketch it? If I moved the graph left 2, which asymptote is that affecting? The VA or the HA? That's going to affect the VA. It's now going to be at x equals what if I moved it left 2? Negative 2. Orale? And if I move the whole thing down 7, that's going to affect the horizontal asymptote, which is now going to be at y equals what? -7. Y'all are awesome. Okay, I think we're ready to sketch this puppy, aren't we? Arf, arf. Yeah. Let's come over here. We'll draw the y-axis. We'll draw the x-axis. What do we draw first? I forget. The asymptotes. Now, your notability will actually sketch dotted lines for you somehow. I forget how. If you click on something. Where the colors are. Oh, yeah. You can pick line quality, and then you can click dashed line or dotted line. Dashed or dotted. I'm going to choose dashed. Okay. And then you can snap a line. So I'm going to go to -2. Here's -1. Here's -2. I'm going to write -2 there with a dashed line. Oops. And then I'm going to come back through and just snap it. Snap it. Look at that. That's a beautiful asymptote. Or you can just draw it by hand. That's what I typically do. All right. And then I'm going to come down here. I'm going to switch to a dotted line instead of a dashed line. And I'm going to come down here to -7. And I'm going to come in and snap a dotted line. Snap. There it is. All right, now enough playing with that. I'm going to go back to my regular writing, and I'm going to write this as -2 in a full color, and I'm going to write this as -7. I do want you to label them as well. But you don't have to snap lines like that. You can just draw it with a dotted or a dashed line. Okay, now notice what I've done here. I've kind of drawn a new x and y axis, haven't I? It's kind of like a new x and y axis. The graph is either going to live in my new quadrants 1 or my new quadrants 3, or my new quadrant 2 and my new quadrant 4. The only thing that's going to put them into a different quadrant is what type of transformation? A reflection, either an x or a y. Either one will do the trick, right? Do we have any reflections here? No. So it has to live in the default quadrants of 1 and 3. So here's how we draw it. We draw it coming from this asymptote, and then somewhere, I don't care where, somewhere you leave that asymptote, and you start curving it and going to the other asymptote. And then this one, we come from this asymptote, we curve it at some point, and we go down towards that asymptote. And there it is. The last thing you could do is label it as g of x if you want. We're done. Let's talk about the domain. What's the domain of G? The set of all x such that x ain't what? Nope. It's going to be where the asymptote is. Look up here. What value of x is not allowed? What value of x when you plug it into x plus 2 gives you 0? -2. -2 is not allowed. What do we have at -2 on our graph? An asymptote. Will the graph touch the asymptote? No. Is it in the domain? No. So your domain is everything except the x value where the vertical asymptote is. Okay? Every other value of x is legal. Now, for the range, we don't really get the range from the equation just yet, but it's the set of all y's such that y is not equal to what y value? What's the only y value this graph never touches? -7. Fantastico. Fantastico. I think that's Italian for fantastic. How do you say spaghetti in Italian? Spaghetti. Let's do end behavior. Let's do this. As x goes to infinity, g of x goes to what? -7? -7? -7, right? What is the left end behavior? As x goes to negative infinity, g of x goes to what? No. Also -7, right? También. Igualmente. -7. It just approaches -7 from above on the right-hand side. So if you want to put a little plus sign there, you can. And as we go out to the left, it approaches -7 from below. You don't always have to put the little plus or negative ionic charge there. That just kind of gives you more information. All right. The end behaviors will always approach the horizontal asymptote value, which is pretty cool. All right. Let's approach the vertical asymptote at -2. As x approaches -2 from the right-hand side, the plus sign means from the right-hand side. What is g of x approaching? Hop on the graph. Start heading towards -2 from the right-hand side. We're getting closer and closer to what? Positive infinity. And then finally, as x approaches -2 from the left-hand side, our y values are approaching what? Negative infinity. Very good. The graph is so important because once you have the graph laid out in front of you, those types of questions, those four, are pretty easy. You just look at your graph that you created where the asymptotes are labeled. Yeah.
If you're doing these two, so you look at it going this way, you do this, these two, you look at it going.
Exactly. Right. If you're looking at, what'd you say, these ways, you go that ways? If you're looking at these ways, you go that ways. Something like that.
Yeah.
Right? Yeah. If you're going to infinity or negative infinity as x, where is x infinity and x negative infinity located? Way down the right-hand side and way down the left-hand side of the number line. So that's what you're looking at. If you're looking at the behavior at the vertical asymptote, you're looking at this right here. Those are the two types of questions we'll ask you, or I'll ask you. Well said, Lauren. Any other questions? It's kind of fun learning new stuff, isn't it? Kinda. Emphasis on kinda or emphasis on fun? Kinda fun or kind of fun? Fun. Kind of fun, right? Yeah. All right, we got time for another one. Oh man, I'm going kind of slowly today, but y'all are having a good time. That's all that matters, right? Riley's dreaming of it. Yep. Rough night. Describe how the graph of 1 over x minus 3 is transformed into the graph of -1 over x plus 2. Okay, so we've had questions like this before. Okay, we're not starting with our parent function 1 over x anymore. Let's think about what this graph looks like. Okay, where is the vertical asymptote for this function?
3.
At 3, at x equals 3. Okay, all you have to do to find the vertical asymptote, if you want to know, real simply, take your denominator and set it equal to 0 and solve. Okay, pretty easy. X minus 3 equals 0, that means x equals 3. So this one starts with a vertical asymptote at 3. I'm just going to draw it like that. And of course, it still has a horizontal asymptote at 0. We didn't move it up or down. So the graph lives here and here. That's kind of what the graph looks like. But the important thing is 3. Okay, now, what does this new one look like? The new one has a vertical asymptote where? -2. You can either do it by setting x plus 2 equal to 0 or saying, oh, x plus 2, we moved it left 2 units. Left 2 units puts it at -2 because it used to be at 0. All right. And then, of course, what does the negative in top do? Any kind of negative multiplier is going to reflect it. This one reflects it across the x-axis, but it lives here now and it lives here. Okay. Now, we're trying to describe how to get from the first one to the second one. So let's talk about, first of all, the horizontal shift. How do I get from +3 to -2? I move the graph what? Left, how many spaces? 5. Yeah. If I move it left 3, that takes me back to 0, plus another 2, silly goose, to get to -2. Right. I've never met a silly goose. Every goose that I meet wants to like tear me in half with its beak. And I'm like, is this a joke or something? And they never laugh. Left 5. Okay, and then there's one last thing we have to do. Left 5, and then what do I do to get the graph from being in quadrants 1 and 3 to 2 and 4? Reflection across the x-axis or just x-axis reflection. There you go. And there's your answer. That's how you get from one to the other. That's how I would recommend doing these problems. Sketch the first one real quickly, sketch the second one, and just look, what do I have to do? Oh, I got to move it left, and then I got to flip it. Got it. Easy. Easy peasy, lemon squeezy sneezy.
Wait, why isn't the x-axis reflection the first step?
You're right, actually. It should be the first step. You caught me in a moment of I wasn't you're yeah.
Well, you get to like
Yes, I will count off. Yeah, I will count off. Yeah. I was not thinking. I was focusing on the vertical asymptotes instead of focusing on PEMDAS. So let this be a warning to everybody. PEMDAS is always in the house. The x-axis reflection comes from multiplication or division. They always have to be done before your addition and subtraction, okay? So we technically have to reflect it first and then move it left 5. Very good. Very good. You got me. I didn't even make 100 on my own quiz. All right. All right. So now I'm going to ask for extra credit. Is there any extra credit, teacher? What can I do to bring my grade up? Thank you, Lauren. Thank you, Lauren. Might need a fire extinguisher back there. You're on fire. Yeah. Be careful. Don't burn yourself sitting too close to Lauren today. Sizzle. We got time. We got time. We got 5 minutes. Yeah. Let's do one more. Let's do one more. This is too much fun to stop now. Identify the asymptotes for the rational function. Sketch the graph. Let's sketch the graph first, or do you want to do the asymptotes first? I don't care. Let's do the asymptotes first. What the crazy hey? Let's do that first. Now, a vertical asymptote is of the form x equals or y equals? X equals. Let's set that up first, and a horizontal is y equals. What is the, whoa, you're fast. I was going to ask what's the only transformation that moves the vertical asymptote. The answer would be a horizontal shift. That's your x minus 5, which moves it right 5, so it's at 5. Or you set the denominator equal to 0. Now, how do we find the horizontal asymptote? What's the only transformation that affects a horizontal asymptote? A up and down. What do we move this graph up or down? 3 up, so it's at y equals 3. So again, for the vertical asymptote, it's kind of the opposite of what it appears. You see minus 5 in the equation, so it's plus 5. Horizontal is exactly as it appears. Okay, we were going to have to identify those anyway when we sketch the graph. So remember, because we graphed those first. So let's go ahead and draw a little x and y axis. We'll come right 5, 1, 2, 3, 4, 5. And we'll draw a little vertical asymptote. I'll just draw it by hand. And then we're going to come up here to 3, a 1, 2, 3, a 1, 2, 3, a 1, 2, 3. Waltz, everybody. 1, 2, 3, 1, 2, 3. There it is. Now, quick question. Does it live in quadrants 1 and 3 or the new quadrants 2 and 4? 2 and 4. How do we know that? Because there's a what? There's a negative, so there's an x-axis reflection. Now, for the 2, that's just a vertical stretch by a factor of 2. Do we really show that on our graph? No, there's no way to show that it's twice as steep, so we just draw it like, oh, stupid highlighter. I haven't done that in a while. It's going to look like this, okay? And it's going to look like this. Now, you can easily answer the domain, right? The domain is everything except 5, and the range is everything except 3. Once you know the asymptotes, you have the domain and range as well. It's not only fun, it's easy. It's what? It's fun easy. Okay, that's a good place to stop. We'll stop with example 3. We got 4, 5, 6, 7, 8, 9, and 10. Holy moly smokers. Yeah. The reason that we didn't get as far in the notes today is because I started up here with a different type of, I didn't just jump in. I gave you kind of a background. Yeah, you're welcome. Okay. Any comments or questions?